Hi guys. So today I'm going to talk about container fundamentals using Docker and Kubernetes. So let's first try to understand what are containers. So if you have seen containers in the real world, you know it has done a significant improvement to how we transport goods through ships. So that is the same concept we are going to use in the computer software industry with the containers. So these containers are Linux containers. So let's try to understand on the physical containers how it has improved the transportation with the introduction of these containers. So in the past, if you want to ship some item from one place to another place using a ship, a cargo ship. So you have to push your item, you have then the ship will load all the different items coming from different people, and when it reaches the destination, it has to separate out the entire set of goods into different people and provide those and process them separately. So during this transformation, there can be so many mix-ups happens. So the management aspect of these goods from like thousands of different people would be really hard when it comes to transporting and clearing out or delivering to the end user. But with the introduction of containers, so you can put whatever you want inside a container, and then when you give the destination address, so the container will be delivered through the cargo ship, and it's pretty easy to clear or deliver to the end user. So it doesn't matter what is actually within the container. So whether it's a small item, whether it's a large item like a vehicle, so it doesn't matter. So you just need to buy a container and put your stuff and then label the destination. So similarly, in the computer world, so it all started with the concept of multitasking. For example, in the initial stages of the computing, the CPU can process only one task. So once it is done, we are handing over this next task. So this is where the computing has run in the batch mode in good old days. Then with the introduction of multitasking operating systems, even though we have a single CPU unit, we divide the CPU time across different processes or different tasks and make it so that multiple tasks are running in parallel. So in theory, at a given time, it will only be running one task, but there will be multiple tasks running parallelly in different states in these multitasking operating systems. But sometimes it is not the best way to run your software. So then it comes to the era of virtual machines. For example, let's say I want to run different operating systems within my laptop. Then I can't run multiple operating systems in the multitasking mode because operating systems are core or the central components which handles the resources of your computer. So that is where you wanted to create virtual machines on top of your operating system. To do that, we use a technology called hypervisor. So whatever the operating system you have in your computer, we call that as the host operating system. That host operating system will run a hypervisor, which is another software layer, and then it will create different virtualized environments to run multiple operating systems. So on top of these virtual environments, you can run your own different applications on top of those operating systems. We call them as guest operating systems. So now you have the host operating system, hypervisor. On top of that, you have the virtual machines. On the virtual machines, you have the guest operating system and the relevant libraries and the applications you want to run. So this virtual machine concept is quite successful and it is used in most places. So if you take the Amazon AWS cloud, EC2 cloud, it also provides you virtual machines, virtualized computing environments with whatever the operating system you requires. So one of the drawbacks of this virtual machine or the virtualized environment concept is so it needs a lot of resources to run the fundamental software, which is the operating systems. So if you create two or three virtual machines within your laptop, you will you will practically see how much of resources each and every guest operating systems are consuming, even though you don't run any applications. So that is kind of wasting the computing resources. So this is one of the key reasons why why this container concept became popular. So even though this Linux operating system or the Linux kernel had this concept of containers using the namespaces and processes for a longer time, it became more popular with the platform called Docker. So what this Docker did with the container model which was available in the Linux is that now you can run multiple applications within the same environment, within the same computer, without installing additional operating systems, but getting the same level of isolation you get when you were running on virtual machines. So how the containers or Docker achieve this capability? So in the world of containers or in the Docker world, you have the host operating system, which is, let's say, Linux. In most cases, it should be Linux. So on top of Linux, there is this Docker engine running, Docker environment, which is basically providing an interface to the applications to create separate runtime environments. We call them as containers to run their own applications while utilizing the same host operating system through the Docker runtime environment. So in this scenario, if you remember the virtual machine based scenario, in the virtual machine world, we have used the hypervisor. And on top of that, we have the operating system and the applications. But in the Docker world, instead of the hypervisor, we have the Docker environment, Docker daemon, and then on top of that, we have the actual applications. We don't need an operating system to run our application. So with this new model, since we don't need a separate guest operating system to run our applications, the resource utilization has been drastically reduced. So another key aspect of Docker is you can package multiple applications into a single Docker image. So in Docker, we have some concepts which we need to understand. So there is a file where you can define what are the components which I am going to bundle into a certain runtime bundle. So this file we called as the Docker file which explains what components need to be bundled into this Docker image. So using the Docker file, you can build a Docker image, which is like a binary, which you can run on top of the Docker runtime. So when these Docker images are actually running on top of the Docker runtime, we call them as containers. So now we have the Docker file, which is the definition of what goes inside the container. Then we have the image, which is the actual binary or the packaging of the runtime components, and the container, which is an image in runtime. Basically, image running on the Docker runtime is called a container. So what are the advantages of this model? As I mentioned, the resource utilization is one key advantage. Another advantage would be now you can run the same container image across different computing environments. Let's say in the past, if you want to run your application in different environments like development, production, UAT, you need to make sure that you configure those relevant parameters based on those environments, and there is no 100% guarantee that the application will run similarly across these environments, because there can be multiple dependencies, multiple versions, different softwares running on those environments. But with the Docker, you can package all these dependencies and the relevant runtime libraries uh, along with the application, and make sure that it runs the same across any environment it runs. It will run the same on your laptop, it will run the same on the development, UAT or production environments. So that is another advantage which the container brings into the table. So another key aspect is like it is flexible. Flexible means you can easily find the Docker images for any popular library or software. For example, let's say you want to create an application which has a front-end application component, you have a back-end application component, and a database. In this kind of a scenario, you can easily find the Docker images for relevant runtime components. For a database, you can easily find a MySQL image, MySQL Docker image, which is officially published by the MySQL. Then you can find Python for front-end development, or for the back-end development, you can find any framework like Spring Boot or Ballerina or any other framework to develop your back-end services. So due to that, it is really easy to build an application and package that into a Docker image. And then another advantage with the Docker is the Docker ecosystem or the Docker repository system. So as I mentioned, people have published these standard Docker images to this Docker repository so that everyone can share these common libraries and common software with each other in a reliable manner, and the users can just create Docker images and run their containers by using the images which are built by other people. So Docker has revolutionized how people build applications and how these development, testing, and production kind of environment upgrades are happening. So let's see whether Docker is enough to modernize our enterprise ecosystems. So what actually happens is, like, let's say you have an application, you in your enterprise you have like 10 different applications you want to deploy. So in the past, You might have deploy all these different web applications in a single Tomcat or J2EE or any web server. But the problem with that approach is if that particular web server goes down, all the applications will be unavailable. And also there is a chance that one particular application can kill the entire web server. In that case, it will impact all the other applications. So due to that, people have decided to divide these functionalities. So that is where the service-oriented architecture or the SOA came into the picture. But in the SOA world, we didn't have the capability, or people didn't realize that running different services again on the same runtime, let's say in a ESB or on an application server, doesn't do much difference to the actual problems we had with these application deployments. So that is where the microservices architecture came into the picture, where each and every application or different functionalities are developed, deployed, and maintained as separate units. So Docker has complemented this requirement and this idea of microservices pretty well. So now you can define your services or the service capabilities as separate microservices and deploy them in Docker containers. Now what? Now let's say you want to scale these applications based on the incoming load. Let's say if you want to increase the number of containers you are running for a certain application, then you want to automatically increase these number of instances. And also you want to monitor this entire container ecosystem. If a container goes down, you need to make sure that it another container pops up immediately. So these kind of requirements drives drives the concept of a container orchestration system. So instead of just running the containers, so when people actually running containers in a large scale, they identified that the container platform needs some improvements or additional features. Things like the scalability of containers, the availability of the containers, and the ability to monitor different containers. So that basically gave or paved the path for the next topic, which is the container orchestration platforms. So Google has been using the concept of containers, microservices for a longer period of time because of their scale of Google's ecosystem. They have been developing an internal container orchestration system called Borg. So this Borg container orchestration platform has evolved into another platform called Kubernetes. So today, Kubernetes is one of the finest container orchestration systems available in the market. So what Kubernetes does is when you define your containers in the runtime, so you need to manage these containers based on different requirements. For example, let's say if you are getting higher amount of traffic to a certain container, you need to make sure that you have enough container instances running on your platform. So Kubernetes can do this automatically with the auto scaling capability. And also if you want to load balance between these different instances, that can also be done with the concept of Kubernetes services. And also, when you want to expose these services into external world, you can use Kubernetes ingress controllers to expose these services which are load balanced through Kubernetes ecosystem. And also it provides ways to define different namespaces and isolate different applications and also control the amount of resources like CPU, memory, which can be used for each and every container. And also it makes sure that if you say like if you want to run 4 instances or 4 containers, 4 instances of a particular application, always Kubernetes makes sure that there will be 4 instances always, regardless of what happens to each and every container. Let's say due to some issues, one container goes down, then Kubernetes will automatically spins up a new instance. So likewise, Kubernetes has made an entire computing ecosystem. For example, let's say a data center into a single single platform. So Kubernetes is like an operating system for data center. You have your computing resources, your servers, laptops. Likewise, if you install Kubernetes on top of these computing resources, you can consider this as a single machine. So on top of the Kubernetes layer, you can ask for computing resources and you can run your applications regardless of the underlying instances or underlying actual computing resources. So each and every computing resource considers as a node in Kubernetes. Let's say if I am connecting my laptop to a Kubernetes cluster, it will be considered as a node. And there are two types of nodes in Kubernetes. Those are the master nodes and the worker nodes. So the master nodes are there to manage and control the entire Kubernetes ecosystem. For example, if one container goes down, the master node will notify the worker nodes through the Kubernetes runtime, which is running on a Kubernetes side, to spawn a new instance of a container. So in Kubernetes, we call uh, a unit of execution as a pod. So pod can contain one or more containers. So pods can be scaled up, scaled down. Pods can be so you can create multiple instances of pods and expose those different instances of the same pod as a service to external parties, and then through ingress controllers you can expose that to outside people as well. So I think these topics have their own different explanations. So they have very detailed information which you need to go through. But for the beginning, so let's summarize what we have discussed for a beginner. So containers have defined a way to run your applications in total isolation without consuming much resources. Then Docker has becoming the de facto standard for running containers, where you can define Docker files, build Docker images, and then run those images in a Docker runtime as containers. Then Kubernetes have provided a capability on top of the container ecosystem so that you can control how these containers are running in your ecosystem, for example, within your data center, transparent of the actual computing resources you are running on top of. So basically, Kubernetes has transformed your data center into a single computing resource so that you don't need to worry about which computer your application is actually running. So if you think about your laptop, if it has 8 cores, when you want to run an application, you don't care which core this application is running. As long as it is running and it is up and it is providing the required information, you are happy. So that's the same kind of capability Kubernetes is providing on top of multiple computers. Okay, so that's it for today's session. I'll catch you up with another session later. Thank you.